Hello there, Mr. Sutton here, bringing you this lesson on Fundamental Theorem Integral Evaluation of Polynomials. In this one, we'll be using the FTC to evaluate definite integrals of polynomial functions, and we'll be solving definite integral problems with missing constants and tables. For your warm-up here, go ahead and find the antiderivative of integral 4x to the 6 dx. And this is just an indefinite integral. All right, let's see how we did. So with these, again, you have to bump up the exponent. So this would be the 7th power, and then divide by the new exponent. So we would have 4 over 7 x to the 7th power. Don't forget the plus c. For those of you wondering why we're even talking about antiderivatives now after just ignoring them for so long, here's the answer to that. The Fundamental Theorem of Calculus has two parts. The first, which we already learned, said that derivatives and integrals are inverses. The second, just as important, is also called the Integral Evaluation Theorem, and this says if you have a function that's continuous on a to b, and let big F represent the antiderivative of f, and we know how to calculate antiderivatives, then the following is true. The integral of your function from a to b is equal to the antiderivative with the upper limit plugged in minus the antiderivative with the lower limit plugged in. So what this is basically giving you is the area under the curve of f between a and b. We're not going to really rigorously prove this, but the intuition behind this, each of these antiderivatives is giving you a kind of area. Big F of b, that's giving you kind of the whole area of somewhere up until you get to b. Big F of a, that's the area of somewhere up until you get to a. If you want the area between them, you just need to subtract the stuff you don't want from the entire area, and that gives you everything in between. There's a notation we have to use on these. Once you've actually found the antiderivative, big F of x, and expressed it in a formula form, we can use brackets or the delimiter symbol to show what we're about to plug the limits into. So once you actually found the antiderivative, you can put it inside a bracket with the limits outside of it here. If you don't like the brackets, you can put this straight line next to it. It's called a delimiter, again with the limits here. And these both mean big F of b minus big F of a. At this point, we're going to take our integral evaluation theorem for a test drive. So to start this off, we need the antiderivative of the integrand here. Pause the video and take a second to find that. All right, so you should have ended up with, if we bump that up, x to the 4th over 4. And I'm going to put these in my square brackets now because this is all going to be evaluated with some limits in there. Next, we've got negative 3x. And I'm going to close the brackets now and rewrite my limits of integration. Now, you might be wondering why I'm not putting the plus c in there that I always have to have with my antiderivatives. And technically, we could put it in there. But what I'm about to do is I'm going to do 2 plugged into all this stuff minus whatever all this is when I plug negative 2 in. Since I'm going to be subtracting two things and they're both going to have c's in them, since we're subtracting, those plus c's are actually going to always cancel in this situation. So although you could write them by convention, we never do. All right, so next step, plug in 2 and negative 2 and see if you can evaluate the rest of this. All right, so we have 2 plugged into all this stuff like so. So 2 to the 4th minus 3 times 2, we still have that 4 down there. Next, we're going to be subtracting, and I'm going to put another parentheses here, negative 2 to the 4th over 4 minus 3 times negative 2. So just a whole bunch of plugging in. You don't have to use the square brackets here. I'm just using them because I cut and paste from up here. You could just use normal parentheses if you wanted. And it's up to you how far you simplify these. If it's a free response, you actually could just leave it like this, and you would be done, and that would be wise. If it's multiple choice or you need the answer for something else, though, then you would keep going. I'm going to keep going. So this is 16 over 4, which is 4, minus 6 gives us negative 2 for that first bracket. And then over here, this is, again, 16 over 4, which is 4, plus 6 is 10. So we're doing minus 10 then. And that all comes out to negative 12. So a lot of these integral problems are just kind of straightforward, take the antiderivative and plug in the limits sort of problems like example 1. But this example shows you some of the other things you can use integrals for. Let's say we have this whole integral equaling 20,
and we have this mystery constant k kind of stuck in there, and we want to figure out what value of k makes this happen. So pause the video, and first let's see if we can take the antiderivative of this stuff in here. All right, so I'm going to write, let's see, this bumps up to a 5. Dividing by that, we have just x to the 5th, starting my evaluation bracket here. And then this bumps up to a 2. Dividing by 2, we have negative 3x squared. And then how about this k? Well, k is actually being treated as a constant. How do we know that? Because this is dx, not dk. So that means that any letters other than x in here count as constants. So that means this is just going to be plus kx, and all of that equals 20. And I've got my limits of integration on my evaluation bracket now. All right, what next? Well, we need to expand all this. Pause the video and take a few minutes to do that and see if you can get the k value. All right, so plugging 3 into all the x's, and again, we know we're plugging 3 into x's because this is dx, not dk. So 3 plugged into all of those gives us this assortment of things. Plugging negative 1 into all of that and subtracting, we have this huge bracket of stuff, and then all that equals 20. This is one of those situations where you have to simplify or you just won't be able to do the problem. So going from left to right, we've got 243 minus 27 plus 3k. And now over here, I'm subtracting all of this stuff. So this is going to normally be negative 1, but I'm negating it, so it's positive 1. Over here, this would normally be negative 3, but that's negated, so it's positive 3. And this negative k here now becomes a positive k, and all of that equals 20. Combining like terms, we've got, let's see, 216 plus 1 plus 3 is 220. We also have a 4k on the left side. Subtracting 220 from 20, that's going to be negative 200. Dividing that by 4, we get k equals negative 50. Here's another example. This time f of x is defined with some values in this table. So pause the video and see if you can use what you've learned so far to figure this crazy thing out. All right, so our first step on these, since we're just trying to evaluate this, we're going to take our antiderivative. So on the left here, the antiderivative of 6 is going to be 6x. Again, our variable is x because it says dx. And what's the antiderivative of 2f prime of x? Well, it's just going to be 2f of x. And we're evaluating that from 3 to 8. So we've got 6 times 8 plus 2 times f of 8 minus 6 times 3 plus 2 times f of 3. And I'm going to do a little more simplifying here. I can't just leave it with f. So we've got 48 plus 2 times, let's see, what's f of 8? F of 8 is 3, so 2 times 3 is 6. And over here we've got an 18, and 2 times f of 3, well, f of 3 is 4, so 2 times that is 8. So 18 plus 8 over there. So this is then 54 minus 26, which is going to come out to 28. For our last trick, we're going to see what happens when we try to take the derivative of something that we've already used the integral evaluation theorem on. So we already had a theorem that tells you what to do in this situation, but instead of following that earlier FTC 1.0, start by using what you've learned today on the stuff inside here, and then take the derivative. All right, let's see how that went. So antiderivative of f would be big F. So we have big F of t from a to x. And now that's going to be plugging in these for t here. I've got big F of x minus big F of a. Taking the derivative of all these, derivative of big F of x is just f of x. How about the derivative of big F of a? Well, a is just a constant, so big F of a is just a constant. And if you take the derivative of just a constant, you get 0. So this does a couple things. First off, it verifies our first fundamental theorem where the derivative of all this stuff is just going to come out to f of x. But it also shows us that it doesn't actually matter what this lower limit of integration is when you're taking that derivative because it just gets differentiated away anyway. Pretty cool, huh? Till next time, this is Mr. Sutton signing off.